So in this short video that accompanies my blog post, I just want to have a quick look at Mistral's new model. And this is called, well, the interface at least is called Le Chat. I'm not going to try any French pronunciation in this, so you can just go to mistral.ai. You can sign up for your free account. That's what I'm going to use here. This is not a paid account. Once you've logged in, this is what you're going to see. And at the top there, you see Le Chat. That would be, akin to just ChatGPT kind of interface. And this is what it's going to look like. On the left-hand side, it might be collapsed for you. You can just open this up. But there's always a big plus button there, and you can just start a new chat. Now, I've already populated this chat. I just want to see how well it does with Python code. And you don't have to watch me type, number one. And number two, you don't have to wait for the response. And one of the things here that you'll notice if I click on this little upload button, it says drop PDFs or images here. So I cannot upload a CSV file. And so what I'm going to do at the moment, just for this free version that has just come out, I'm just going to test some Python code, and we're going to look at a system of linear equations, and can we use one of the packages that is not very often used, sympy, the Symbolic Python package, see if it can help us code. So I've started the new chat. Just want to show you if I do start a new chat, there is 3 buttons here at the bottom. So I did click on this canvas button, and that is perfect for creating code. So let's go back to this chat that I've already had. Let's see where I got going. I said, please write the Python code using matplotlib. So I wanted to use a package to extend the usefulness of base Python to create 2 lines. Now, if you look carefully, what I've done here is I've used LaTeX or LaTeX to indicate the mathematical equations. So if you know LaTeX, great. If not, it's a very easy language to learn. And I'm going to say language in inverted commas. So y sub 1, so that underscore means we're going to have a subscript 1 equals 1.2 times x minus 1. And y sub 2 equals negative 1.3x in the plane. Now, look at that response. It said, sure, below is the Python code using matplotlib. And you can see that slightly different font there. So it's probably rendering something like Markdown, putting little tick marks in front of and following matplotlib to get that different notation to create 2 lines. And look at this. We see the mathematical typesetting. So y sub 1, y subscript 1 equals 2x minus 1, and y sub 2 equals minus 1.3x in the plane. So first of all, a win for me is that it can read this LaTeX notation. And that's very useful if you are entering any kind of formulas when you're using any of these large language models. So there's the response I got, and it's very easy. There's a little copy and paste button up there. And I'm going to copy that in my code editor. I'll do that in a short bit, but let's have a look at this at the bottom. This code will generate a plot with 2 lines corresponding to the given equations. The np.linspace function is used to create an array of x values ranging from negative 10 to 10. So I decided that all on its own, that would be a good interval. And the equations for y sub 1 and y sub 2 are defined accordingly. The plt.plot function is used to plot the lines, and additional functions like plt.title, plt.xlabel, and plt.ylabel, and plt.legend, and plt.grid are used to add titles, labels, and legends, and a grid to the plot. Finally, the plt.show is called to display the function. So with a little bit of Python background, that should make good sense. Let's go to my code editor, and I'm using VS Code. As always, I've already created a new notebook. I've set up a virtual environment in which I have installed matplotlib and numpy. If you do not know what I'm talking about, no problem. I do have extra videos that explains how to set up a virtual environment in VS Code for Python, and I do that on a per project basis. I do not add any packages to my base installs of Python on any of my systems. And so I've created a new code cell. So you just hover in between any of these cells, you can add code. And I've pasted the code that I received from the new or the Mistral chat feature. And so that's just copying, just a plain copy and paste, and I'm going to run this section, and there's our output. Our output shows these 2 lines representing a linear system of 2 equations, and of course where we see the intersection is going to be a solution to both of these equations. We see a nice grid, we see the legend there, and nice choices of color so that we can identify the lines in the plane for these two equations. We can also see some nice LaTeX typesetting in the title and in the legends there, so I think that's a pretty good job. Let's go back to the chat. Next up I said thank you, that worked well. Always have to compliment your large language model. So then I wrote, now please show me how to use sympy, that's the Symbolic Python package, to create an augmented matrix to present the linear system of the two linear equations in the previous plot. And that was the response, sure. You can use the sympy library, again notice there the different font, library to create an augmented matrix for the linear system of the two linear equations y sub 1 equals 1.2x minus 1 and y sub 2 equals negative 1.3x. And this was very nice. It said, first let's write the equations in standard form. And that's where we have all the variables on the left-hand side and the constants on the right-hand side. So it's rewritten equation number 1 as negative 1.2x plus y equals 1 and 1.3x plus y equals 1. So it's simple algebra writing it in standard form. I love that. And there's the code. I'm going to look at the code shortly. Let's have a look at the rest of the response. The code will create the augmented matrix given the system of linear equations. The sp.matrix function is used to create the matrix, and the equations are converted to standard form before being added to the matrix. So the augmented matrix will look like this. That's very well done. That's using the pipe symbol there just to denote that this is an augmented matrix. So we do see the coefficients on the right hand side. And it says this matrix represents the coefficients of the variable. There we see the two coefficients for x and y on the left side and the constants on the right hand side. And so let's copy and paste that code and see what it does. So there we go. I've pasted it in this new code cell. It says import sympy as sp. Now that's not standard. Usually we use sym. Remember, that's just your choice. There's not a rule that says we cannot use sp, but usually most of us in the Python community would use sp when we import scipy. That being said, then we define these two variables x and y, and we set them as the symbols, the mathematical symbols x and y, using the symbols function inside of sympy. That's very nice. It then uses the EQ or the equation function in sympy. So we see sp dot, we imported sympy as sp, so we have to reference it using that namespace abbreviation sp dot equation. There's the left hand side of my equation, comma, the right hand side. It does that for both. Then it uses the matrix. There we go, the matrix class that creates an instance of the matrix class. So you can think of that as a function that instantiates that class, and we see sp.matrix, and it's our parameter here is a list of lists, and it is row by row that's entered, and then it displays our augmented matrix to the screen. So that looks good to me. Let's have a look at the result, and there we can see beautiful mathematical typesetting of our augmented matrix. Great, then I said thank you. Can you show me the sympy code to solve the system, system of linear equations? And it said certainly. You can use sympy to solve the system. It's given me the code again, and it tells me this code will solve the system of linear equations and display the solution. The sympy.solve or sp.solve function is used to solve the system, and the equations are defined using the sp.eq or equation function. Let's break down the steps. Import the sympy library, define the symbols x and y, define the two equations, use sp.solve, display the solution. The solution will be the values x and y that satisfy both equations. And so if we copy and paste that code across, there we go. I've just deleted that import sympy as sp because it's already in this active document. And so the rest of the code is there, and it prints it out. X is 0.4. and y equals negative 0.52. We see the solution. Remember, that is where we'll see the intersection of those two lines. But when I wrote these problems, that's not exactly what I wanted. We have an augmented matrix, and we can use elementary row operations or Gauss-Jordan elimination, and we can create a reduced row echelon form of this matrix. We know that we are going to get a unique solution to the system. We see the solution there, in fact, but we know that because we saw that we have an intersection between our two lines. So I went back to Mistral and I said, thank you, could you rather show me how to solve the system of linear equations using sympy by calculating the reduced row echelon form of the augmented matrix that you created? And Mistral reported back, and it said, certainly you can use sympy to solve the system of linear equations by calculating the reduced row echelon form, or RREF, of the augmented matrix. Here's the Python code to do that, and it tells us that this code will be used to calculate the reduced row echelon form of the augmented matrix and display it, breaking down explanation. And then it says here is the complete code with comments. And so it's done a little redo there. Let's copy and paste that. And I do have it there. Let's have a look at it. And we see the result there. What I do not like is that it does the print function there. And the print is always going to ignore the mathematical typesetting and give you back this matrix notation with a list of lists. So if you just get RREF underscore matrix, which is the augmented matrix or the reduced row echelon form that we calculated without the print function, you can see the mathematical typesetting. And as you can see, the coefficients, at least, that gets reduced to an identity matrix, and you can simply read the two results. So 1 times x sub 1 plus 0 times x sub 2, that's going to give you, or then at least x plus 0y is going to give us negative 0.4, meaning x is negative 0.4, and 0x plus 1y equals 0.52. In other words, y equals 0.52. That's similar, the exact same results as we got from using the solve function. So that is great. Do remember that once we've created our matrix of coefficients, or augmented matrix at least, with the constants, we can just use the RREF function there, but we use it as a method, which is just applied to the object, the matrix object that was instantiated. And that gives back 2 objects, and so we use 2 variables here. So Mistral's actually identified that quite correctly. You do get these 2 objects back. Let me just show you if we then do pivot columns. You see we get the tuple back of the pivot columns. So that is great. Let's go back, and it actually gives us a little bit of explanation. What does a reduced row echelon form look like? If there were indeed unique solutions here, we'll get on the left-hand side, at least as far as the coefficients were concerned, we get that back as an identity matrix, and we just read off the values of x and y on the right-hand side. So that was just a trivial little example. I could not upload a CSV file just to do some statistical analysis, but I think just it's very good, at least in this, as I say, simple example, just to do some Python code. I gave it a little bit of a stretch by inserting some LaTeX code, and I did, get it to use one of the packages in Python that is not used very often, although I absolutely love it and use it all the time myself, and that's the Symbolic Python package, sympy, and it did a very good job, especially after I prompted it to use linear algebra or linear algebra approach to solving this linear system.